Hey there, math fans. I'm Dr. Andy Lovelace. I have a lot of materials on Taylor series. I've taught this for 20 years. I've taught over 21,000 students. But I realize that among the applications and the error bounds and the things I've done, I don't have very many things where I just go through and show the patterns, because that's something I do in lecture. But that got me thinking, maybe I could make a bunch of short videos where I talk about the patterns for several functions. The pattern for the Taylor series for either the x and sine and cosine. And as I started to think about putting that together, I thought, well, if I did that, I think I could include in there just enough theory to give a little more background. So this is interesting to you. That's what I'm going to do here. I'm going to do a little kind of quick snapshot of Taylor series. So let's go. So I'm going to start with e to the x. At the end of this, I will explain where this is coming from and how we can understand this. But what I've written here is an exact formula that says these two things are actually equal, provided you can take derivatives, a few things, and that the error is precisely given by this integral. That's not something we usually tell students. It's part of a proof. It may be plus or minus, depending on whether it's even or odd, but I'll show you that in a moment. But there's actually a precise value of this. So why don't we tell students to compute this? Why do we do this so-called error bound? So I thought I would just show you an example. So here's e to the x. If this were e to the x, the nice thing about e to the x is its derivative is itself. So if you plug in 0, you get 1, and this is a 1. And I had an instructor in grad school that just said all this is a clothesline to hang your derivatives. And by doing this, you actually make the functions match up. You make it so they have the same height, the same first derivative, the same second derivative, the same third derivative. And the factorials out in front are canceling these powers if you were to take the derivative so that the derivatives match. That's kind of the explanation I give in class. I go into that in some more detail. So if you go all the way through and talk about this error. So here I just picked a random large number. So if you go all the way up to 71, it is extremely close to the graph. I'm going to show you this real quick. So here is my function. Apologies, I grabbed the wrong thing. Here is this function. Let's make it real big just for a moment. Oh my gosh, where did that fat head go? So let's look here. So what I have here is the e to the x graph. That's the black curve. And I have the tangent line. That's the green. And I put in a little red thing to show you the error. And that's at about 3. So that's the error at 3. If I go to so that's 1 plus x. If I go to the second one, I get this parabola. Notice what happened to the error. It got smaller. If I go to the third one, that's the error. And then the fourth, and then the fifth. If I go to, so it's 4th, 5th, 6th, 7th, 8th, 9th, it hugs the graph. In fact, I have to zoom way out to see it's getting closer. This is the 20th Taylor polynomial that you're looking at. What I just wrote was the 71st. I'm not even going to show you that because I don't think it'll be able to handle it. It's going so far out. So the error gets really small. We can see that. Surprising fact. This is very useful in many applications. But and for me, that's what's interesting. We can find this pattern and it works. And you can kind of just take it at that. But in our course, we talk a little bit about error bound so that we can give a more solid foundation to this. And again, I'll talk about this in a moment. But here's what this actually would look like in our example. So you'd have this plus or minus depending on the sign. This would be the next derivative, which in this case I can actually write down. You rarely can write that down, but it's e to the t. This would be a 71 factorial. This would be a 71. So somebody said, well, what if I only am going to use this between -3 and 3? I'm zoomed into that. It'd be better if I just had a number here, a number that quantified how accurate. Is it going to be accurate to 3 digits or 4 digits or what? But I can't really do that. And that's not a nice integral to compute So somebody had the idea of, well, let's just replace this by the biggest it can be. And on this interval, that would be e to the third. When we do that, we are finding a bound on the next derivative. I know that sounds scary. That's the thing we call m. But if we do that, we can pull it out. Now, the moment we pull that out, it's no longer equal at all. It's just an approximation. So we're approximating this thing. So that thing is definitely less than or equal to, I'm just talking about that integral, e to the third over 71 factorial. But that really simplifies things a lot. It's a little funny to look at because there's an x here, but we're really integrating t minus 10 to the 71. That we can integrate. There's going to be a 72. We can plug in our x, we can plug in our 0, we can put absolute values. And so all of that can be simplified if we're willing to be less precise and just write e to the third over 72 factorial, because it's 72 from integrating, x to the 72. So we can think of that as this plus or minus error. Now when we did that, we lost precision. We had to find this m, this maximum over the interval. If we want to go a step further, we can replace this with a 3 to say, well, that's the biggest this can be. So that can give me a number in this spot. And I didn't even compute it because I think it's going to be extremely small. And that's the other piece of this. Why is it going to be extremely small? Because 3 to the 72 is ginormous. That's not a word. But it's 3 times itself 72 times. So why am I so confident that this is a small number? Well, 72 factorial is more giganticer. That doesn't make any sense. Because it's 72 times 71 times 70. And that's why this, Taylor's inequality, this error bound, is good enough to prove that it's going to 0 because this is getting so big. All right, so that may or may not have helped students. On my future videos, I will just find the patterns, but I am going to finish this up by saying a little bit. So this does get closer and closer to 0. This approaches. At that moment, we're like, all right, enough of that. And we just put ... And then we replace this with equals in the sense that we're talking about. And then at some point, our hands get tired and we decide, well, maybe we can use some notation here to make our lives easier. 1 over k factorial x to the k. And there are so many things I could say about this. My favorite is that you can plug in 1 and get that e is 1 plus 1 over 1 factorial. Now that's 2. Plus 1 over 2 factorial. Now that's 2.5. 1 over 3 factorial. And this just gets closer and closer to the value of e. In fact, that's probably one of the best ways to approximate it. Okay, so that is our first example of a pattern we can find. And I'll do this for the other functions as well, and maybe I'll do a couple we don't normally do. I'll just kind of sample them one by one. I may not do this all this quarter. I just wanted to try that with this added little error bound. Now, I said I'd say something about where that's coming from. It's coming from a clever use of integration by parts. I don't often do this in a ton of detail in class because it just confuses students so much, but because we're doing a video, you can turn it off. So it comes from this clever idea that this is the same as this. That's the fundamental theorem of calculus. If you integrate a derivative, you get this. The clever idea is to do integration by parts, not to make things simpler like we normally do integration by parts for, but to try to make the derivatives appear, to try to make the Taylor polynomials appear. And so we call this u, and we call this dv, and we integrate, and that makes this worse and this better. There is a subtlety which most students would not put an x here. They would just put this. And almost always when we do integration like this, we choose the constant to be 0. It works out nicer if you choose this constant to be negative x, because when you plug in the 0, then things line up better. So that's the part I always don't like about this proof. I find it hard to motivate that. But you evaluate. After you evaluate, you move this over, and there is the first Taylor polynomial. and we're looking at the difference between them. And there is our first example of this integral I'm talking about. So there is a precise way it's done. It's this integration by parts. I started to try to like write an example up with sine and cosine, like try to show you an example with a function, but I realized that did not add any clarity. But if something like this helps, I basically did integration by parts to make this worse, to sort of show the principle of what's happening. And this is the tangent line. This is it. But the real thing is, then you could do it again. If you did it again and you integrate, you get a 1/2 and you get the third derivative. If you do it again, then you get a 1/2 and a 1/3 with the fourth derivative. So that can be extended. It's what we would say is you'd prove it inductively, the next one from the previous one, to get this. And then in general, we can say that's going to be less than or equal to m over n plus 1 factorial from the integrating x to the n plus 1. And then something similar can be done if it's based somewhere else besides 0. Okay. So that's the pattern. That's our first pattern. As I've told students, error bounds are not the fun part, but they give us a foundation for those moments when you want to be precise. For me, just the interesting thing is that we have this now. I would argue that the following function, 2.71828182 ... to the x, is terrible to work with. If you're on a desert island, you have to square that. You're going to do a big multiplication. I would argue that it's better to work with this. 1 over 1. It's more user-friendly. And this was the debate of the 1700s a bit, from the bit of history I've read, that are we allowing this to be a function? Are these perfectly good functions? So they were uncomfortable with this too. But I would argue that this is better than this. Certainly for some things. Better as an analysis tool, better if you're computing by hand. In fact, it's the sort of thing that your calculator uses to compute it. So being able to write a function this way actually is really valuable, and it can be used to do many things. The example we always give is like if you were integrating something that really mattered to you, like this comes out of integrating the bell curve. This gives you a way to do it. There's really no fast way to do this. You'd have to use some sort of approximation technique. And probably the easiest approximation technique is to just take this and substitute it in all these places, simplify and integrate. And that gives you the answer in a pretty good way. It approximates it very quickly. So that's a quick example. So I'm plugging in a negative x squared. Negative x squared squared, so it's going to become x to the fourth. And at any point you could just stop and say, that's good enough for me. And then you could integrate that. And that requires very little effort to integrate. 3x cubed plus 1 over 2 factorial 1/5 x to the fifth. Plug in a 0 and 1, and you get 1 minus a third plus a tenth. And that's going to be really close to what this is, because I know that approximates it very quickly. If it's not good enough, we could just add a few more terms until it's close enough. If we want to know the error, we could go back and compute it. Often we don't compute the error, we just check each step to see that it's getting better. So that's the idea. If this is interesting to you, I can do a similar thing for sine and cosine and arctangent and log, and just look at the patterns. Those would be faster videos. All right, hope that's interesting.